The second way that you can specify what a digital circuit needs to do is by providing a truth table. Now, the truth table has a row for every possible combination of the inputs. Here you can see that there are 3 inputs. Each input can take on 2 different values, so there are 2 to the third, or 8 rows in the table. These 8 rows will always appear in the same order if it's a 3-variable problem, and so you'll become accustomed to this order. If you don't have it memorized, write it somewhere that's easy for you to access, because you're going to need to write the same order over and over again. You'll notice that the C column alternates once every row, the B column alternates every other row, and the A column alternates every 4th row. That's a nice shortcut for remembering how to write it. There's also a column that corresponds to the output, and so you can see the output for every possible combination of the inputs. If a Boolean algebra expression is like a shopping list, a truth table is more like a list of every possible item in the store with the word yes or no next to it, indicating whether or not you need to purchase that item. And so it's very exhaustive. It's also exhausting in some cases, but it does list every possible combination. As a result, this means that it contains all the information that a Boolean algebra expression had. So really, a truth table and a Boolean algebra equation, they're exactly equivalent to each other. So it is very helpful for us to be able to know that if you have one, you can go back to the other, or vice versa. And we saw last time that we can go from a Boolean algebra equation in sum of products form into what we call a 2-level logic. And so having that 2-level logic circuit is our goal here as well. So the question is, can we convert this truth table into a sum of products expression? And the answer is yes, we can. What we need to do is look at the rows that contain a 1 as the output. So you can see here in this example, there are 3 rows that contain 1s as the outputs. I'm going to take each row one at a time. So here you can see this corresponds to A equals 0, B equals 0, and C equals 0. Or I could write that as not A, and not B, and not C. So anywhere that there's a 0 for the variable, you put a bar over the variable. And here you can see 1, 0, 0. Well, then the A is a 1, therefore it doesn't get a bar, but B and C are both 0, so they do get bars. Here it's 1, 0, 1, so it's A and not B and C. So you can write a product expression for each row that contains a 1 in the truth table. So notice that those products are the 3 rows where the output should contain a 1. In other words, F should be 1 if this row is active, or if this row is active, or if this row is active. And of course, what we just said there was that we're going to calculate the product terms. We have here 3 product terms, and we're going to OR them together. So that's a sum of products. So the sum of products is simply going to take these 3 terms, which I identified by looking at the rows that contain 1 at the output. Then every time that the A, B, and C contain a 0, I put the variable with a bar. If they contain a 1, I put the variable without a bar. Then I'm going to OR those terms together. This is how you can convert from a truth table directly into a sum of products expression. So I'm going to scroll down here to the expression that corresponds to that term. So you can see here we have not A and not B and not C, or A and not B and not C, or A and not B and C. That's an expression that can be used to implement the function that was shown in that previous truth table. And here's the circuit that you can use to do that. Because remember that we said any Boolean expression in sum of products can always be represented in 2-level two-level circuit. So I'm going to look here. I'm going to see that there's 1, 2, 3 products. That means that I need to have 1, 2, 3 AND gates. And each one of those products has 3 terms in it. And so each one of these AND gates is going to have 3 inputs. And then similarly, because there are 3 products, we're going to combine them together using an OR gate that has 3 inputs. I would begin by drawing the AND gates, and you know how many they're going to be and how many inputs they are. And then I would draw the OR gate, because that's just lumping them together. Then you can come back and fill in the left half of the circuit. The left half of the circuit is the hardest part to draw, because you got all these wire crossings. I mean, there's a lot of stuff going on in here, and it gets kind of complicated to trace all the inputs. But essentially, we know that we're going to need to have 3 inverters. Because at various points, both A, B, and C are all going to be inverted or not inverted. So you're going to have the 3 inverters, and you're going to just draw off of each variable at the appropriate place to either get it be inverted or not inverted. So we can go from the truth table to the SOP expression, and then from there to the digital circuit. This completes the design process. But if I were you, and if I were handing this design off to my boss, I'd be a little bit embarrassed, because this is really not a great design. I think that we can do better. So how can we do better? We're going to do better by applying Boolean algebra. You might say, but I don't like Boolean algebra. And I say, I agree, but Boolean algebra makes a huge difference for us when we're improving this system. So what I'm going to do here is, looking at the expression up here, I'm going to look at the second and third terms. You have A and not B in both of those terms. So I'm going to factor the A and not B out of those terms. And you can see here that I have A and not B, and then I'm going to and with not C or C. Those are the two terms that were left behind. Well, anything ORed with the inverse of that is going to be equal to 1. And then anything ANDed with 1 is just going to be that thing back again. So the and 1 is going to go away. I'm left with not A and not B and not C, or A and not B. Let's factor in not B out of both of those terms. I end up with this expression. And then let's look at this one. This one's a little bit harder. We have a theorem that says A or not A and B equals A or B. That's the one that we proved 3 different ways in the first lesson that we learned about Boolean algebra. If we applied that, where B is equal to C bar and A is just equal to A, we end up with this expression right here. So we've actually reduced things down substantially from the original version. Remember that the original one had three input AND gates. Now we're down to just an AND gate and an OR gate. Notice how much simpler this solution is than the one that appeared in figure 4. And all it took was a little bit of application of Boolean algebra to make our lives a little bit better. I would be proud to show this solution to my boss, and I think that you would be too. So at this point, you're ready to solve the designing a digital circuit from a truth table example. I would encourage you to do that. Then come back and I'm going to show you a shortcut for some cases of designing from a truth table.